Try to imagine you're standing on a straight road and you start driving without stopping, 100 kilometers per hour, day after day, without sleeping, without resting, and you keep doing this for many years, then many centuries, and even millions of years, and you still haven't crossed the diameter of Jupiter, a planet more than 140,000 kilometers wide. At this point, the problem is no longer the numbers. It's that you can't actually feel it, because your brain was never designed to understand things on that scale. It's only used to the distances you can travel in a day, not the kind of distances that even light takes time to cross. And when we leave the solar system, when we start talking about planets that are larger, lighter, and stranger than anything you've ever imagined, your intuition isn't just wrong, it becomes completely useless. And that's when the real story begins, because the planet we're about to talk about will force you to confront a very uncomfortable truth. You have never truly understood what size really means. For most of the 20th century, the way we understood planets was actually quite simple. And if you put yourself in the shoes of the scientists back then, it made perfect sense, because all we had was our own solar system. And from that, we built what seemed like an obvious model. The bigger a planet is, the heavier it is, and the stronger its gravity. The classic example is Jupiter, with a mass about 318 times that of Earth, and a radius of about 69,911 kilometers, a benchmark that made everything feel consistent and easy to understand. For decades, there was no reason to doubt this model, because every planet we observed followed the same logic, from Saturn to Uranus. But if you look a little closer, you start to see a deeper problem. This entire model was built on an extremely small sample of data, just a handful of planets in a single system, and we unconsciously assumed that this represented the entire universe. I want you to pause right here for a moment, because this is exactly where intuition starts to trick you. When you take a familiar example and stretch it to infinity, physics never promised you that what's true in the solar system would be true everywhere else. And even when we didn't yet have enough observational data about planets around other stars, the laws of gas, heat, and gravity themselves already pointed to a very clear possibility. If you place a gas planet close enough to a star and heat it to temperatures of thousands of Kelvin, its structure would no longer resemble anything you've seen before. And at that point, the issue is no longer that we haven't observed enough. It's that we were far too confident in a model built from a very special case. And that is how every scientific model begins to collapse. Not because it's completely wrong, but because it's no longer sufficient to describe reality. But now, let's go one step further, not with imagination, but with what we have actually observed since then. Because there is a planet called HET PP67b, announced by the HETNet project, and if you look at its numbers, you will immediately understand why all your previous intuition no longer holds up. This planet has a radius nearly twice that of Jupiter, that is around 140,000 kilometers, a size that, if placed in the solar system, would dwarf every planet you've ever known. And if you stopped there, you would automatically conclude that it must be extremely heavy, with enormous gravity. But that's exactly where you make the mistake, because its mass is only about 0.34 times the mass of Jupiter. And that leads to an even more astonishing number. Its average density is only about 0.06 grams per cubic centimeter, much lower than water, and even lower than many porous materials you can hold in your hand. And if you want to picture this more intuitively, think of a giant balloon inflated to the point where there's almost nothing inside, a structure that could be deformed by even a small change. But what makes this even more serious is that this is not a hypothesis. It is the result of two completely independent measurement methods that have been verified multiple times. The first is the transit method, where astronomers measure the tiny drop in the star's light as the planet passes in front of it, from which they derive the radius with very high precision. The second is the Doppler effect, where the star's very slight motion, caused by the planet's gravity, is detected through shifts in the light spectrum, allowing us to calculate its mass. And when you combine these two measurements, you don't just have two separate numbers. You have a complete picture of a planet that is extremely large, but extremely light, orbiting its star in just about 4.8 days. That means it lies very close to its main energy source, where temperatures can easily exceed 1,500 to 2,000 kelvins, hot enough for the gas to expand to the point where it nearly escapes the planet's own weak gravity. And this leads to an important consequence. The planet is no longer a stable structure, but a system that is being stretched, heated, and may be gradually losing material into space. And at this point, you have to face a very uncomfortable reality. There is no error in these measurements, no mistake in the data. What is wrong is the model in your head. Because this is not just a large planet. It is a clear physical paradox, proof that the rules you once thought were obvious simply do not apply at this scale. And that's when you realize the problem isn't that the universe has become irrational, but that the way you understand it has never really been complete. And if at this point you start to suspect that maybe all these numbers are just speculation, that is a completely reasonable reaction. Because we can't fly to HETP 67b. We can't take direct pictures of it the way we photograph Jupiter. So the most important question right now is, how do we know these things with enough accuracy to trust them? The first method, and one of the most powerful ones developed since the early 2000s, is called the transit method. The idea is actually very simple but extremely clever. When a planet passes in front of its star, it blocks a very small portion of the star's light. And this drop in brightness can be measured with extremely high precision by modern telescopes, often just a few parts per thousand, or even a few parts per 10,000. From that drop in light, you can calculate the area of the planet's surface that is blocking the light, and from there derive its radius, because the geometry here is very clear. The more light is blocked, the larger the planet. And the important thing is that this method barely depends on any assumptions about the planet's internal structure. It relies only on light and pure geometry. But size is only half the story, because to understand the planet, you need to know its mass. And that's where the Doppler effect comes in, a technique developed since the mid-20th century and widely used in astronomy. In it, we measure the very small change in the wavelength of the star's light as it is pulled back and forth by the gravity of the orbiting planet, like a very slow dance that you can only detect through extremely subtle changes in the light spectrum. When the star moves toward you, its light is shifted toward the blue, and when it moves away, the light is shifted toward the red. From the amplitude of this wobble, you can infer the mass of the planet, because the heavier the planet, the stronger it pulls its star, and the clearer the signal. What's important here is that these two methods are completely independent. One is based on blocked light, the other on the star's motion. And when both lead to the same conclusion, you begin to have a very high level of confidence that you're not being fooled. These observations are usually repeated many times over multiple orbital cycles, sometimes lasting months or years, to make sure the signal isn't random noise. The data is also often confirmed by multiple different telescopes, from ground-based observatories to space telescopes, each with its own errors, but when combined they minimize the overall uncertainty. Scientists also use statistical models to test the chance that the data is noise or misinterpreted, and only when the probability of error is low enough is the result published. And when you put all of this together, you realize that we are not measuring a planet with a single method. We are building a picture from multiple layers of independent data, each one cross-checking the others, and it is this overlap that creates high reliability. And if that picture looks absurd, if you're looking at a planet twice the size of Jupiter, but much lighter, then that doesn't mean the data is wrong. It means your intuition is being seriously challenged. Because science doesn't care what seems reasonable. It only cares about what is actually happening. And sometimes that is much more unsettling than you think. What makes all of this truly uncomfortable isn't how we measure things, but how you interpret those numbers. Because your intuition almost always links size with mass, a larger object must be heavier and must have stronger gravity. And this is completely true in the everyday world you live in, where everything you touch is solid, or at least has a relatively stable structure. A bigger rock is heavier. A bigger truck is heavier. And even when you think of familiar planets like Earth or Jupiter, the rule still seems to hold, because they have enough mass to hold their own structure together. But what you don't realize is that this rule depends heavily on the state of matter. And when you move from solid to gas, everything starts to change in a way your intuition can't keep up with. Gas has no fixed shape. It expands when temperature rises. It contracts when pressure increases. And most importantly, it can occupy an extremely large volume without needing much mass. And this is exactly where a planet like HETP 67b steps in and completely shatters every assumption you've ever had, because it is much larger than Jupiter in size, but significantly lighter in mass, a combination that if you relied only on intuition you would consider impossible. Try to imagine you have two objects in front of you. One is twice as large as the other, but only half as heavy. In everyday life, this almost never happens, but in the universe, under completely different conditions, it doesn't just happen, it has been clearly observed. The easiest way to picture this is to think of a balloon. When you blow it up, its size increases very quickly, but its mass only increases by a very small amount because of the air inside. And if you keep blowing it to the extreme, you end up with a very large but very light object, a structure that can be deformed or burst by even a small change. Now expand that image to planetary scale, where temperatures can reach thousands of Kelvin, where gas is constantly heated and expanding, where gravity is not strong enough to hold everything tightly together. And you will begin to see that a planet can inflate like a giant balloon blown up to its limit. In the case of HETP 67b, the average density is only about 0.06 grams per cubic centimeter, much lower than water, and even lower than many porous materials. This means that most of its volume is empty space between gas molecules, not dense matter. And when you realize this, you begin to understand that size is not a reliable measure of mass, at least not in this context. Because what you're looking at is not a tightly compressed block of matter, but an expanded, fragile structure that depends heavily on temperature and pressure. This also leads to another important consequence. The gravity on the planet's surface is not as strong as you think. It may even be much weaker than Jupiter's, and that allows the gas to continue expanding outward, creating a feedback loop where larger size leads to lower density, and lower density allows the size to keep increasing. This is not a small exception. It is a sign that the rules you trusted no longer apply. And when you try to apply familiar intuition to a completely different system, you will always reach the wrong conclusion. In the end, what matters is not whether this planet is large or small, heavy or light, but that it forces you to accept that the way you understand the relationship between size and mass is incomplete and in many cases completely wrong. Density is where everything starts to become clearer, but at the same time, it is also where your intuition is completely broken, because in physics, density is simply mass divided by volume, a formula so basic you can write it in a single line, but its consequences are far more profound than what you're used to in daily life. In your world, everything seems to follow a very stable rule. A larger object is usually heavier because it contains more material, and the density of familiar materials doesn't change much. For example, water has a density of about 1 gram per cubic centimeter, and this has almost become an invisible standard you use to compare everything else. Rock, metal, wood, all have densities a bit higher or lower than water, but still within a range you can sense. And this very stability creates the illusion that the world always follows a simple logic. But when you step out of that familiar environment and look at a planet like HETP 67b, you are forced to confront a number that if you just glance at it, you might overlook. But if you stop and think, it completely shatters the way you understand matter, because the average density of this planet is only about 0.06 grams per cubic centimeter. That is only about 6% the density of water. And that means most of its volume is not dense material, but empty space between gas molecules. Try to imagine holding a piece of sponge or foam in your hand, where most of the space inside is air and the actual material only takes up a very small portion. But even those objects usually have higher densities than this number. This shows just how empty this planet is, far beyond any experience you've ever had. And when you expand that idea to planetary scale, you start to see the problem. The planet's size is determined by the volume it occupies, but its mass is not large enough to fill that volume the way you would expect. The result is a giant object that is almost hollow, a structure that, if you relied only on intuition, you would consider impossible to exist. This also explains why the planet's gravity is not as strong as you thought, because gravity depends on mass, not size. And when the mass is not large enough, it cannot compress the gas into a denser structure. Instead, the gas continues to expand outward, forming a very thick and extended atmosphere. And this is where you begin to see an interesting feedback loop appear. Low density allows gas to expand. Gas expansion increases volume. Increased volume reduces density further. And the process continues until it reaches a delicate balance between gravitational force and thermal pressure. What's important here is that nothing in this process violates the laws of physics. Everything follows equations we have known for a long time, but the final result is completely unlike anything you've ever seen in daily life. And that is precisely why the big but light paradox is not actually a paradox in physics. It is a paradox in your perception, because you are trying to apply a model built from solid, stable objects to a dynamic, hot and expanding gas system. Once you understand the role of density, you start to see that size is no longer a reliable indicator of the amount of matter. A planet can become gigantic, not because it contains more matter, but because that matter is spread out over a much larger volume. This also helps you understand why planets like this often exist close to their stars, where high temperatures provide the energy needed to keep the gas in a state of continuous expansion. And when the temperature drops, this structure shrinks and becomes more like what you're familiar with. In the end, what you must accept is that density, a concept that seems so simple, is actually the key to explaining the entire phenomenon. And once you look at the world through density instead of just size, you will see that what once seemed absurd is actually just the natural consequence of the laws of physics. The real mistake was the intuition you brought with you from the beginning. Gravity is where everything becomes clear in a very uncomfortable way, because it forces you to completely abandon the idea that size determines the strength of a planet. In reality, gravity depends only on mass and distance, not on how large an object looks. This sounds simple when you say it, but it is extremely difficult to accept when you apply it to a planet like HCTP 67b, because you are looking at a giant object, larger than Jupiter in size, but with a mass of only about 1/3, and that means the gravity it generates is much weaker than what you would expect. In your familiar world, a larger object almost always pulls harder, but here that rule is completely broken. The result is a planet where, if you stood on it, you could feel much lighter than you imagine, even though you are standing on a structure larger than anything you've ever known. To understand this more deeply, you need to think about a very important concept in astrophysics: escape velocity. It is the minimum speed a particle needs to reach to escape the gravity of a celestial body without being pulled back. This number depends directly on the mass and radius of the planet. On Earth, escape velocity is about 11.2 kilometers per second, while on Jupiter it reaches about 59.5 kilometers per second, a number that reflects its strong gravity. But when you apply the same formula to HETP 67b, you get a very different result, because although the radius is large, The low mass significantly reduces the escape velocity. And this has an extremely important consequence. The gas molecules in the atmosphere, which are always moving due to temperature, are much more likely to reach speeds high enough to escape into space. And when you remember that this planet orbits very close to its star, with a period of only about 4.8 days, you also understand that it receives an enormous amount of energy, which can push the temperature up to thousands of Kelvin. This high temperature increases the average speed of the gas molecules, making it easy for them to exceed the planet's weak escape velocity threshold. The result is that the gas is no longer held tightly, as in the case of Jupiter, but is continuously leaking out into space, not in an explosive way, but in a slow but steady flow, like a balloon with a leak that you cannot see with the naked eye. This creates a structure where the outer part of the planet does not really belong to it in a strict sense, but is in a transitional state between being held and being lost. That is why scientists often describe planets like this as dynamic systems, not static objects. And if you look at this process over long periods of time, you will see that the planet is not a fixed structure, but an entity that is evolving. It may gradually lose mass over time as gas is blown away by stellar radiation. This also means that its current state is only a temporary phase, a delicate balance between weak gravity and strong thermal energy, where any small change could significantly alter its structure. And this is where you must accept a very important point. Gravity is not only the force that holds everything together, but also the factor that determines whether a planet can maintain its structure or not. And when that force is not strong enough, you don't just have a light planet, you have an unstable planet, a planet that is on the boundary between existence and disintegration. And that leads to an uncomfortable conclusion. Large size does not guarantee stability, and in many cases, it only hides an extremely fragile structure inside. Temperature is the next piece that makes the entire picture clear, but at the same time much more frightening. Because if you really want to understand why a planet can become as ridiculously large as HATP 67b, you cannot ignore the role of the thermal energy it receives from its host star. When a planet orbits very close to its star, completing one orbit in just a few days, it does not just receive more light, it receives hundreds of times more energy than Jupiter receives from the Sun. And that pushes the temperature of its atmosphere to levels that can exceed 2000 Kelvin, a number that, if you convert it to everyday experience, means almost nothing you are familiar with could survive under those conditions. At this temperature, gas molecules are not only moving fast, they are moving extremely fast, with speeds high enough to resist the planet's weak gravity. And this is where you begin to see a very important mechanism appear: thermal expansion. In physics, when a gas is heated, its molecules move faster and push farther apart, increasing the volume. This is a basic law that you can observe in even the simplest experiments. Think of a balloon. When you heat the air inside, it expands, not because you added more material, but because the molecules inside take up more space. Now imagine that process happening not in a small balloon, but in a planet hundreds of thousands of kilometers across, and you will begin to understand what is happening. The planet's atmosphere does not just expand a little, it is inflated on a gigantic scale, creating a layer of gas that extends far from the core and increases the planet's radius without a corresponding increase in mass. This explains why you can have a planet twice the size of Jupiter, but lighter, because most of that volume is not tightly compressed material, but gas in an expanded state. And when you combine this with the weak gravity we talked about earlier, you have a system where nothing is strong enough to hold the gas tightly together. The result is that the planet becomes an extremely extended and fragile structure. What is important to understand here is that temperature does not just change the state of the gas, it changes the entire structure of the planet, because when thermal energy is large enough, it can counteract gravity and lift the gas higher, making the planet larger in size. And this does not happen once and stop. It is a continuous process where energy from the star constantly supplies heat, keeping the gas in an expanded state, while gravity tries to pull it back, creating a dynamic equilibrium. If you lower the temperature, the planet would shrink, becoming smaller and denser, more like what you are familiar with in the solar system. But under current conditions, the high temperature keeps it in an inflated state, almost at the limit of stability. And this is where you begin to see that the size of the planet is not a fixed property, but the result of a battle between thermal energy and gravity, a battle in which, in this case, heat is winning. This also explains why super-puffed planets are usually found very close to their stars, because that is the only place with enough energy to maintain this state. If they were farther away, they would quickly shrink and lose their special characteristics. When you look at the entire process, you realize that temperature is not just a number describing the environment. It is the central factor that determines the structure of the planet. And if you ignore it, you will never understand why a planet can be so large yet still unbelievably light. In the end, what you must accept is that the gigantic size of these planets is not a sign of strength or stability, but a sign of an extreme state where physics is operating at limits that your intuition cannot keep up with. And it is temperature, not mass, that is the main factor controlling the shape you are trying to understand. Radiation from the host star is the next factor that pushes this system beyond all familiar intuition. And if you think temperature alone is enough to explain everything, you are still missing a very important part of the story. Because the energy that a planet like HP67b receives does not come only in the form of heat, but also in the form of high-energy radiation, including ultraviolet and X-rays, types of radiation that can interact directly with the atomic structure of the gas. When these high-energy photons collide with molecules in the atmosphere, they do not just heat the gas, they can knock electrons out of atoms, a process called ionization, turning neutral gas into plasma, a state of matter where free charged particles move about. This is extremely important because once the gas is ionized, it no longer behaves like normal gas. Instead, it becomes sensitive to electromagnetic fields and stellar winds, streams of charged particles continuously ejected from the star at speeds that can reach hundreds of kilometers per second. You can picture this as a storm that never stops, but instead of air-wind, it is a stream of plasma slamming directly into the planet's atmosphere. And because the planet's gravity is not strong enough to hold on to the outermost layer of gas, these particles begin to be pulled out into space. This process is called atmospheric escape, and in extreme cases, it can happen at very high rates, enough to significantly change the planet's mass over time. Real observations show that some planets of this type can lose millions of tons of material every second, a number that, if you try to imagine it, has almost no comparison in daily life. When the gas is blown away, it does not disappear immediately. Instead, it creates long streams of material, trailing behind the planet, like a giant tail, similar to the tail of a comet but on a much larger scale, sometimes stretching hundreds of thousands of kilometers. This means you are no longer looking at a planet with clear boundaries, but at a system that is leaking material into the surrounding space, a structure where the outer part does not really belong to it in a stable way. If you compare it with Jupiter, you will see the clear difference, because Jupiter has gravity strong enough to hold on to most of its atmosphere for billions of years, while here the combination of high temperature, strong radiation, and weak gravity creates an environment where material is continuously lost. And this leads to a deeper consequence. The planet is not a fixed object, but a process, a state that is evolving over time, where its current structure is only the result of a temporary balance between incoming energy and lost material. If the gas loss process continues for long enough, the planet could shrink, becoming smaller and denser, or even lose most of its gas layer, leaving behind a core that is completely different from what you saw at the beginning. And this completely changes the way you should think about these planets, because the gigantic size you see is not a permanent feature. It may only be a stage in its life cycle, a stage where it is inflated by heat and at the same time eroded by radiation. When you look at the entire process, you begin to realize that radiation is not just a secondary factor, but a shaping force, one that can determine whether a planet keeps its material or gradually loses it. The important conclusion here is not that this planet is strange, but that it is showing you a basic mechanism of the universe, where energy from a star can alter the structure of a planet on a large scale. And in this case, that change is strong enough to make the planet no longer a stable entity, but a system that is continuously transforming, where every second that passes contributes to reshaping its form and mass. And that is why, when you look at it, you are not just looking at a planet, you are looking at a process happening right in front of your eyes. The familiar image you have carried from the beginning, that a planet is a round sphere, stable and with a clear surface like Earth or even like Jupiter, is actually a very strong simplification of reality. And the problem is not that it is wrong, but that it is only true within a very narrow range of physical conditions. When you apply that same image to a planet like HATP 67b, you are trying to force a familiar concept onto a completely different system, and the result is that you start misunderstanding it from the very beginning, because in this case there is no surface in the sense you are used to. There is no sharp boundary where you can point and say the planet ends here. Instead, you have a continuous transition where the density of matter gradually decreases as you move away from the core, from dense gas near the inside to extremely thin gas on the outside, eventually blending into the surrounding space with no clear boundary at all. If you imagine approaching this planet, you would never land like on Earth. Instead, you would gradually sink into an increasingly thick layer of gas, like entering an ocean with no clear water surface. This means that the concept of the planet's radius, a number we often use to describe size, is actually just a convention, usually defined at a certain pressure level, for example 1 bar, equivalent to Earth's atmospheric pressure. But that is only a convenient marker for measurement, not a real physical boundary. And when you remember that these super-puffed planets have extremely low density, you will realize that most of their size lies in the extended atmosphere, a layer that can stretch tens of thousands of kilometers beyond the core, very thin and very easily affected by temperature and radiation. If you could see this planet directly, you would not see a sharp sphere with clear edges. Instead, you would see a cloud of gas fading into space, where light from the star behind it could pass through in places, creating an unstable and hard-to-define image. This is not just a visual problem. It reflects the real physical structure of the planet, where pressure and density change continuously with distance, with no sudden jumps, no hard shell, and no surface for you to stand on. As you go deeper inside, pressure gradually increases, temperature gradually increases, and the gas becomes denser. But even there, you still do not have a stopping point, only a gradual change from one state to another. This is completely different from the way you understand a rocky planet like Earth, where there is a clear surface separating the atmosphere from solid material. And it is precisely this difference that makes your intuition useless. Another way to look at the problem is that you should not think of the planet as an object with a definite shape, but as a region of space where matter is more concentrated around a center. But that concentration gradually decreases as you move outward, like a giant cloud held together by weak gravity. And when you combine this with what we have seen about high temperature and strong radiation, you begin to understand that the outer part of the planet is not only thin, but also constantly changing, being stretched, blown away, and replaced by material from inside, creating a dynamic structure rather than a static one. This also explains why planets like this easily lose material, because there is no solid shell to hold everything together, only a continuous gradient where molecules at the edge can easily escape. When you look at the entire picture, you begin to realize that the concept of planet you have carried from the beginning is actually a simplified model built from very special examples in the solar system, where physical conditions create stable and easy to understand structures. But when you step outside those conditions, the definition starts to blur. In the case of HATP 67b, you do not have a sphere in the strict sense. You have an extended system where boundaries are unclear, where the structure is unstable, and where most of what you call size is actually a thin layer of gas being stretched out into space. The final conclusion here is not that this planet is strange, but that the way you define a planet is too simplistic compared to reality. And when you are forced to abandon that familiar image, you begin to see that the universe is not built from the clear shapes you expect, but from continuous gradients, blurry structures, and boundaries that never really exist in the way you imagine. Comparison is the fastest way for you to realize where you've been wrong, and in this case, nothing is clearer than placing ATP 67b next to Jupiter, the largest planet you are familiar with, a benchmark that for decades has shaped the way we think about giant gas planets. Jupiter has a mass of about 1.9 pax 1027 kilograms, 318 times that of Earth, and with a radius of nearly 70,000 kilometers. It is already a gigantic structure by any intuitive standard. But what is more important is that its average density is about 1.33 grams per cubic centimeter, a number that shows its material, even though it is gas, is still tightly compressed by strong gravity. This means Jupiter's atmosphere is not a thin layer that can easily be blown away, but a thick, stable system held firmly by a gravitational field strong enough to maintain its structure for billions of years. When you move to HATP 67b, you immediately see a completely different picture, because although its size is significantly larger, potentially nearly twice Jupiter's radius, its mass is only about 1/3, and that leads to an extremely low average density of only about 0.06 grams per cubic centimeter, more than 20 times lower than Jupiter's. This difference is not just a technical detail, but a complete reversal of intuition, because you are looking at an object that is larger but looser, less bound, and more easily deformed. HTP 67b's gravity is not strong enough to keep its atmosphere in a tightly compressed state like Jupiter's, and the result is that the gas can expand far outward, forming an extended atmosphere that is easily lost under the influence of heat and radiation. If you imagine Jupiter as a thick, solid rubber ball, then HATP 67b is like a balloon inflated to the point where it is almost transparent, where the structure is held together only by a very weak force. This leads to a paradox that you cannot resolve with ordinary intuition. A larger planet that is less stable, a planet with gigantic size, but without the corresponding weight to hold everything together. And this is the point where you must accept that the solar system is not a universal standard, but only one specific case among countless possibilities that physics allows. Everything you learned from Jupiter, from Saturn, from the other familiar planets is true in their context, but not necessarily true under all other conditions in the universe. When you rely too heavily on these familiar examples, you unconsciously build a mental model that you believe is universal, but in reality is only local. HTP 67b shows you that when you change conditions such as distance to the star, temperature, and mass, you can create completely different structures that if you only looked at the solar system, you would never have predicted. This also has an important consequence for the way we do science, because it reminds you that models are not absolute truths, but tools built from limited data. And when the data changes, the model must change too. The conclusion here is not that Jupiter is no longer useful, but that it is not enough to represent everything. And if you try to understand every planet through the lens of Jupiter, you will make a mistake right from the first step, because the universe has no obligation to follow what you are familiar with. It only follows the laws of physics, and those laws allow far more possibilities than you imagine. One of the most common misunderstandings when you think about giant planets is the assumption that if something keeps getting larger, it will eventually become a star. But in reality, physics is much more complex, because for a celestial body to become a star, it does not just need to be large in size. It needs enough mass to compress its core to the point where nuclear fusion begins. The process of turning hydrogen into helium and releasing enormous energy. This limit is not vague, but quite clear, usually lying around several dozen times the mass of Jupiter. And before reaching the threshold of a real star, there is an intermediate region that astronomers call brown dwarfs, with masses from about 13 to 80 times that of Jupiter, large enough to trigger some weak fusion reactions like deuterium burning, but not enough to sustain stable hydrogen fusion like stars. These objects are not planets in the traditional sense, but they are not fully stars either. And they show that mass, not size, is the factor that determines the nature of a celestial body. When you return to HATP 67b, you see another paradox appear, because although it has an extremely large size, even much larger than Jupiter, its mass is far too small to approach the brown dwarf region, and that means it cannot become a star no matter how big it gets. But what is more interesting lies on the opposite side of the issue, because if you continue to make a light planet like this expand even further, you do not create a star, you only make it increasingly fragile, because gravity is not strong enough to hold that expanded structure together. When the gas is heated and expands too much, density drops, escape velocity decreases accordingly, and the ability to retain the atmosphere becomes weaker, leading to material easily being lost under the influence of radiation and stellar wind. This creates a completely different limit from the mass limit, a limit on expanded size, where a planet cannot continue to puff up forever without starting to lose the very material that makes it up. You can think of this like a balloon blown beyond its limit. It does not become heavier, but moves closer to the point where its structure can no longer be maintained. And in the case of super-puffed planets, that point is determined by the balance between temperature, radiation, and gravity. If the energy from the star is too great or gravity is too weak, the planet will not be able to hold onto its extended gas layer and will begin to shrink or gradually lose material. This means there is a natural limit to the maximum size of a planet, not because it cannot be larger, but because it cannot exist stably if it is larger. And this is where your intuition needs to be adjusted once again. Because when you think about the largest planet, you might imagine the heaviest, densest, strongest object. But in reality, it is the opposite. The largest planets in terms of size are often the lightest ones, with the loosest and most easily disrupted structures. The important conclusion here is that size is not a sign of strength or durability, but in many cases, it is a sign of imbalance, a state where the system is being stretched by opposing forces. And when you look at planets like HATP 67b, you are not just seeing a large object, you are seeing a system that is very close to the limit of what it can sustain, where even a small change could alter its entire structure. What you have just seen with HATP 67b is not yet the limit of strangeness, because as astronomers continue to observe, they discover that the universe does not just repeat similar cases, but creates even more extreme variations. For example, WASP-17b, a planet with a radius nearly twice that of Jupiter, but with a density of only about 0.8 grams per cubic centimeter, a number still much lower than water, and belonging to the same family as the super-puffed planets we have been talking about. This means HATP 67b is not a single exception, but part of a group of planets whose structures are dominated by high temperature, weak gravity, and strong radiation. But if you think that was the end, then the Kepler-51 system will make you think again, because in this system there are planets whose average densities are so low that they are often described as cotton candy, with values that can drop to about 0 free grams per cubic centimeter. That means most of their volume is almost empty space between gas molecules. To put this into a more familiar perspective, the air at sea level on Earth has a density of about 1.2 kilograms per cubic meter, equivalent to about 0.022 grams per cubic centimeter. And although these planets are still denser than air, this comparison shows you are getting very close to the limit where a planet begins to resemble a cloud more than a traditional object. What is important to understand is that no laws of physics are being broken here. Nothing is violating the basic principles we know, because everything that is happening is simply the consequence of the same equations that describe gas, heat, and gravity, only applied under conditions that are far more extreme than what you are familiar with. When you change the distance to the star, raise the temperature to thousands of Kelvin, reduce the overall mass, and allow the gas to expand, you open up a space of possibilities that you previously did not think about, and these planets are simply points in that space. This leads to an important realization. The universe is not only larger than what you imagine, but also different in a qualitative way. It does not just expand what you already know, it creates structures that your intuition is not prepared to understand. Every time a new planet is discovered, especially one that lies outside familiar models, it does not just add a data point, it forces us to adjust the way we think, to expand our models to include cases we previously considered impossible. And this is a process with no clear stopping point, because each new discovery often does not make the picture simpler, but instead makes it more complex and stranger, with more exceptions and more edge cases. The conclusion here is not that we are getting closer to a final answer, but that we are discovering that our original question was too simple. And when you look at planets like WASP-17b, or the members of the Kepler-51 system, you are not just seeing strange objects. You are seeing a reminder that the universe was not designed to fit your intuition. And every time you think you have understood it, it presents a new example to prove the opposite. Everything you have just seen is not just a few interesting exceptions, but a clear sign that the entire system of intuition you rely on to understand the world is completely collapsing when you step into cosmic scales. Because the rules that seemed obvious, bigger means heavier, larger means stronger, or bigger must mean more stable, simply no longer hold true. You have seen a planet larger than Jupiter but lighter. A planet that can be inflated by heat and at the same time eroded by radiation. A planet with no clear surface and that cannot even hold on to all of its own material. And each of those examples does not just surprise you, but directly contradicts the way you feel the world should work. What is important to understand is that this feeling is not truth. It is only a biological tool, because your brain was not designed to understand the universe. It was designed to help you survive in a very specific environment on Earth, where distances are a few meters to a few kilometers, where objects are solid or liquid, where gravity is almost constant, and where simple rules are enough for you not to have to think too much. To achieve that efficiency, your brain constantly simplifies reality, removes unnecessary details, and creates easy-to-remember general rules like bigger means heavier. And for most of daily life, these rules work so well that you never question them. But when you take those rules out into space, you start to see the problem, because the universe is not bound by the conditions that created your intuition. It operates according to basic physical laws, and those laws allow outcomes that your intuition cannot predict at all. Intuition is not a scientific tool. It is not built to test hypotheses or handle complex data. It is only a quick prediction system based on limited experience. And when that experience no longer applies, intuition does not just become useless, it becomes a source of error. This is why in science, when there is a conflict between feeling and data, the answer is always clear. Data wins, not because we like it more, but because it is measured, verified, and repeated independently. Planets like HATP-67b, WASP-17b, or the members of the Kepler-51 system do not exist because they seem reasonable. They exist because they have been observed using multiple different methods, from transit to Doppler, and every measurement points to the same conclusion. This leads to a very profound shift in the way you should think. You cannot demand that the universe makes sense according to the way you feel, because your perception is not the standard. It is only a byproduct of evolution. When you look back at everything that has happened, you will see that every step deeper into the universe increases the gap between intuition and reality. From size, density, gravity, temperature, to radiation, everything works in ways you cannot predict if you rely only on feeling. This does not mean the universe is chaotic or irrational. On the contrary, it is extremely consistent. It is just that this consistency exists at the mathematical and physical level, not at the intuitive level. Once you accept this, you begin to understand that the goal of science is not to make the world easy to understand in an emotional sense, but to make it accurate. And sometimes that accuracy comes with having to accept that you cannot visualize what you know. The uncomfortable but necessary conclusion is that you cannot rely on feeling to understand the universe, because your feelings were built for a very small and very specific world, while the universe is much larger, much more complex, and much more different. And when you try to apply familiar rules to a reality that does not follow them, you will always reach the wrong conclusion. Understanding the universe is not about feeling it, but about accepting that there are things you cannot feel. You can only know them through science. And the very moment you accept that is when your old intuition truly collapses, making way for a new, more accurate understanding that is also much less comfortable. Numbers are what you trust most when intuition fails, but it is precisely at this scale that numbers also begin to betray you in a very subtle way. Because when you hear a value like 140,000 kilometers to describe the size of Jupiter, or even larger for HTP 67b, your brain does not actually see it. It only recognizes that it is a large number and stops there. You can repeat the number accurately. You can compare it with other numbers, but you have no corresponding experience to connect it to reality. And that is where understanding begins to become an illusion. Try a different approach. Instead of thinking in kilometers, think in terms of light, which travels at about 300,000 kilometers per second, fast enough that in daily life you consider it instantaneous. But even at that speed, light still needs about half a second to travel the circumference of Jupiter, meaning to go around the planet once, something that in your intuition should be instant, but in reality takes a measurable amount of time. This is not because light is slow, but because the size is so large. And when you expand that thought, you begin to see something interesting. At this scale, even the fastest things you know start to become slow. But even when you switch to such units, you still do not truly understand, because you are replacing one abstract number with another abstract number, and your brain still has no anchor to hold on to. You can say half a second and feel it is more familiar, but you still cannot picture a planet so large that light takes a significant amount of time to go around it. This is why converting to familiar units often does not help you understand better. It only creates the feeling that you are getting closer to understanding. The reality is that your brain has a very clear limit in processing scale. It works well with small numbers that can be experienced directly, but when the numbers exceed a certain threshold, they become meaningless on an intuitive level. This leads to an important consequence. You can know a lot of numbers about the universe without actually understanding anything about it. You can memorize Jupiter's radius, the distance to stars, or the sizes of exoplanets, but all of that exists only as symbols in your head, not as images or sensations. And when you begin to realize this, you see that large numbers do not automatically create understanding. They only create the illusion of understanding, a feeling that you know something just because you can repeat the information. This is one of the biggest challenges of science when talking about the universe, because we are forced to use language and numbers to describe things that humans cannot experience directly. And as a result, there is always a gap between what we say and what we actually understand. The conclusion here is not that numbers are useless, but that you cannot rely on them alone to create intuition, because they were not designed for that purpose. Understanding the universe is not about accumulating larger and larger numbers, but about accepting that there are scales you cannot imagine, and that true understanding lies in recognizing that limit, rather than trying to overcome it by adding more numbers. The brain you are using to try to understand all of this was never actually designed for that purpose. And this is not a metaphor. It is a very specific biological fact, because throughout hundreds of thousands of years of evolution, the main task of the human brain was only to help you survive in a limited environment, where important decisions involved detecting danger, finding food, remembering paths, and interacting with objects within a very small range. In that context, understanding a distance of a few meters or a few dozen meters was extremely important. Evaluating the speed of a moving object could mean the difference between life and death. But understanding a distance of millions of kilometers, or visualizing the size of a planet like HPP 67b, provided no survival advantage at all. So the brain did not evolve to handle those things. You may be very good at throwing an object and predicting where it will land. You can estimate distances in a room almost instantly. But all of these abilities are based on direct, repeated experience in a stable environment, and they quickly become useless when you try to apply them to scales you have never experienced. When you hear a number like 140,000 kilometers, or when you try to imagine a planet larger than Jupiter but lighter, your brain does not actually create an image. It only processes it as a symbol, a string of numbers not attached to any sensory experience. This creates a very large gap between knowing and understanding, because you can know the number, you can repeat it, but you cannot feel it. And what is important is that this is not a personal failure, or because you lack ability. It is a biological limit, a limit built deep into the way your nervous system processes information. When you feel that these concepts are too large, too abstract, or not real, that does not reflect the complexity of the universe as much as it reflects the limits of the tool you are using to understand it. That is why science does not try to make the universe intuitive. It tries to make it accurate by using tools that do not depend on intuition, such as mathematics, measurement, and modeling. When scientists talk about the density, temperature, or escape velocity of a planet, they are not trying to visualize it the way you visualize an object in daily life. They describe it with equations and data, things that can be correct even when they are not intuitive. This creates a gap between what you know and what you feel, and that gap is not a problem to be solved, but a reality to be accepted. In many cases, scientific understanding does not bring intuitive comfort. You can know something is true and still feel that it does not make sense, and that does not make it wrong. When you look back at everything we have gone through, from size, density, gravity, temperature, to radiation, you begin to see a repeating pattern. Every step forward in understanding requires you to let go of part of your intuition, because intuition only works well within the range it was designed for. This does not mean intuition is useless. It is still very powerful in everyday situations. But when you step into fields like astronomy, where the scales and conditions far exceed human experience, you must switch to other tools. And this is the key turning point, where you stop trying to feel the universe and begin to accept that there are things you can only understand through data and theory. This also explains why science sometimes feels cold or alien, because it does not try to fit the way you perceive the world. Instead, it forces you to adjust the way you think to match reality. When you accept that, you not only learn more about the universe, but you also learn something about yourself, that your ability to understand does not lie in intuition, but in the ability to go beyond it. And the final conclusion here is not that you cannot understand the universe, but that you cannot understand it in the way you understand the everyday world. You must accept a different approach, an approach where accuracy matters more than feeling, where data matters more than intuition, and where not being able to visualize it is not a failure, but a sign that you are reaching the real limits of human perception. Super puffed planets like HETP 67b are not the end of the strangeness, but only an easily visible example in a long list of phenomena that the universe creates when physical conditions change. And if you expect that after everything we have seen, the rest of the universe will become more familiar, then you are repeating the very mistake your intuition made from the beginning. What is important to understand is that physics is not broken in any of the cases we have discussed. The laws of gravity, thermodynamics, and gas motion still work exactly as we know them. But when you change the initial conditions, change the distance to the star, change the mass, composition, and surrounding environment, the results can be so far from intuition that you feel like you are looking at a completely different system. Jupiter and the planets in our solar system are not the standard of the universe. They are only a special case, a stable configuration within a very large set of possibilities that physics allows. And when you leave those conditions, you can no longer rely on old experience to predict what will happen. When astronomers began observing other star systems, they discovered planets that orbit their stars in just a few days. Planets with extremely eccentric orbits, systems with many planets lying very close to each other, or systems whose structures are completely unlike anything in the solar system. And each such discovery further weakens the assumption that what we are familiar with is common. This leads to an important realization. The universe is not only much larger than what you imagine, but also fundamentally different. It does not just expand what you already know. It creates structures that you cannot infer from familiar examples. Part of the problem lies in our tendency to generalize from limited data. For a long time, the solar system was the only data we had, so we unconsciously treated it as representative of the entire universe. But when new data appears, we are forced to adjust that view. And what is even more important is that we are still in a very early stage of the exploration process, because exoplanet detection methods only really became powerful from the late 20th century. And even with modern tools, we have only observed a very small portion of the galaxy, let alone the entire universe. Each newly discovered planet is not just a number added to a list, but a test for current models, an opportunity to check whether what we think we understand is really true under different conditions. And in many cases, the answer is not entirely, because each new discovery often opens up more questions instead of closing them. When you look at the entire picture, you begin to see that our understanding of the universe is not a complete system, but a model that is being built gradually, piece by piece, with each new piece sometimes forcing us to adjust the old pieces. This does not make science weaker. On the contrary, it is a sign of its strength, because it shows that we are willing to change when new data appears. The important conclusion here is not that the universe is chaotic or impossible to understand, but that what we currently know may be only a very small part of the truth, a part seen through still limited tools and still developing models. And when you accept that, you begin to understand that the strangeness you see is not an exception, but may be the rule, and what you call normal is only a special case in a universe that is far larger, more diverse, and more complex than any intuition you could bring from Earth. Science exists precisely because of the limits you have just seen. Not to make the world easy to understand in terms of feeling, but to describe it accurately even when you cannot visualize it. And this begins from a very simple but extremely important principle. Science does not rely on intuition. It relies on measurement and models. When scientists talk about a planet like HATP 67b, they do not ask whether it seems reasonable. They ask what the data says, what the measurements show, and whether those results are consistent with the laws of physics. This creates a clear separation between perception and understanding, because in many cases you will have to accept that something you know is true even when you cannot feel that it is true, and that is a very difficult shift for ordinary thinking. At the center of this approach is mathematics, because mathematics allows you to describe things you cannot imagine visually. It provides an abstract but precise language where the relationships between quantities are represented clearly and independently of feeling. When you write an equation describing how gas expands with temperature, or how gravity depends on mass and distance, you do not need to see it in your head. You only need to know that the equation has been verified and produces results that match observations. This means equations can be correct even when they are completely contrary to your intuition. And in fact, in many of the most important cases in physics, that is exactly what happens. Remember what we have seen. A planet can be larger than Jupiter, but lighter. A planet can have no clear surface. A planet can have its material blown away into space. None of these feel right, but they are still valid results of physical equations. This is the greatest strength of science. It is not limited by the way you perceive the world. It allows you to go beyond your experience, beyond your intuition, and access parts of reality you cannot directly observe. When you use measurement and models, you build a picture of the universe not based on what seems correct, but on what can be tested and repeated. This also explains why science can correct itself, because if a model no longer fits new data, it is replaced or adjusted, not because it feels wrong, but because it no longer accurately describes reality. In this process, intuition is not completely eliminated, but it is placed in a secondary position as a supporting tool rather than the final standard. You can use intuition to form initial ideas, but you cannot rely on it to confirm what is true. When you accept this approach, you begin to see that scientific understanding does not require you to visualize everything. It only requires you to understand the relationships between quantities and to trust the evidence. This creates a different kind of understanding, one that is not intuitive, but very powerful, because it is not limited by personal experience. The important conclusion here is that understanding does not need intuition, and in many cases, intuition is even an obstacle, because it makes you expect the world to fit what you are familiar with. When you let go of that expectation and accept that the universe can operate in completely unfamiliar ways, you open up the possibility of understanding things you previously thought were impossible. Science does not make the universe simpler. It makes you capable of facing its complexity without having to oversimplify it. And it is in that capability that you find a deeper form of understanding, not based on feeling, but based on accuracy. There is another way of looking at things that you are forced to accept if you want to understand everything that has been said so far. And it begins by completely reversing the problem. The universe is not too large. You are too small to understand it in an intuitive way. Every feeling of gigantic that you experience when thinking about a planet like Jupiter or extreme worlds like ATP 67b is actually not a property of those objects, but your reaction when comparing them to yourself. You never say something is large in an absolute sense. You always implicitly compare it to the size of your body, to the distances you can travel, to the world you are familiar with. And when that difference becomes too great, you call it unimaginable. But that says nothing about the object itself. It only says something about your limits. If you change the reference point, if you imagine a cognitive system that exists at a different scale, things you consider gigantic could become normal or even unremarkable. And this is not a far-fetched hypothesis, but a way to realize that every evaluation of size is relative. The laws of physics do not care whether you see something as large or small. They have no concept of gigantic. They only describe how mass, energy, and forces interact with each other. This means that at cosmic scales, what you call extreme may simply be a normal case within a much wider range of values. When you look at a planet with a radius of hundreds of thousands of kilometers and feel it is beyond your ability to imagine, that is not because it is special in an absolute sense, but because your brain has no experience to compare it to. This also explains why the same phenomenon can be described accurately with mathematics, but remain completely non-intuitive, because mathematics does not rely on comparison to humans. It describes relationships independently of the observer. When you begin to accept this perspective, you realize that the problem is not that the universe is too complex or too strange, but that your cognitive tools were not designed to handle those scales and conditions. This completely changes your viewpoint, because instead of trying to make the universe easy to understand by pulling it closer to intuition, you begin to understand that intuition itself needs to be expanded or even set aside. When you manage to do that, what previously seemed absurd begins to become consistent. Not because it becomes simpler, but because you stop imposing wrong expectations on it. A large but light planet is no longer a paradox, but a natural result of specific physical conditions, a point in the space of possibilities that physics allows. What is important here is that you must abandon the idea that human experience is central, that what you are familiar with is the standard by which everything else should be judged. When you accept that you are only a very small reference frame in a very large universe, you begin to see that feelings like too large, too far, or unimaginable are not descriptions of reality, but descriptions of your limits. This does not make the universe smaller or easier to understand, but it makes the way you approach it more accurate. The final conclusion here is not that the universe is a strange place that needs to be explained in your way, but that it is a system that operates completely independently of you. And the real problem lies in the fact that you are trying to apply cognitive tools designed for a very small world to a reality that has no obligation to fit them. And when you realize that, you not only understand more about the universe, but you also understand that the greatest limit does not lie out there. It lies in the very way you perceive it. Once you accept that the problem lies in the way you perceive things rather than in the universe itself, the next step becomes unavoidable. There is no natural intuition for cosmic scales. There is no innate sense that can help you understand distances of hundreds of thousands of kilometers, planetary masses, or extended atmospheric structures that you have never experienced. Every intuition you have was built from a very specific environment on Earth, where everything falls within a narrow range of sizes, temperatures, and forces. And when you leave that range, intuition not only loses its effectiveness, but also begins to lead you in the wrong direction. You have seen this repeated many times, from a planet like HETP 67b being able to be large but light, to it having no clear surface, and even losing material into space. All of these things are not only hard to visualize, but also directly contradict what you feel is reasonable. And this is the key point, that feeling is not a reliable standard. It is only an evolutionary tool optimized for a very small world. This means that all real understanding of the universe cannot be built from intuition. It must be rebuilt from the ground up through science, through precise measurement, model building, and continuous verification. When scientists study distant planets, they do not ask whether they make sense. They ask whether the data is consistent, whether the measurements can be repeated, and whether physical models can explain those observations. This creates a fundamental shift in the way you approach knowledge, from trusting feeling to trusting evidence. Intuition in this context is not only useless, but can systematically mislead you, because it makes you dismiss possibilities simply because you cannot visualize them. You may feel that a planet larger than Jupiter, but lighter is impossible, but the data shows it exists. And when that happens, your only choice is to abandon intuition, not the data. This is a foundational principle of science. When there is a conflict between feeling and observation, observation is always right. Logic and data become the only standard you can rely on, because they do not depend on personal experience. They can be tested, repeated, and independently confirmed. This also explains why science can go so far, because it is not limited by what humans can perceive directly. When you accept this approach, you begin to understand that understanding the universe is not about expanding your existing intuition, but about building an entirely new system of understanding, where intuition is no longer the foundation. You must learn to work with numbers you cannot visualize, models you cannot see, and results you cannot feel. This is like learning from the beginning again, not because you have lost old knowledge, but because that knowledge is not sufficient to apply in the new context. Every step forward in understanding requires you to let go of part of your intuition and replace it with a way of thinking based on evidence. This process is not easy because it goes against the way your brain wants to operate, but it is the only path to approaching reality at this scale. The final conclusion here is not that the universe is too complex to understand, but that the way you initially tried to understand it was unsuitable. And when you change your approach from feeling to science, from intuition to data, you not only understand things that previously seemed impossible, but you also realize that understanding the universe is actually a process of rebuilding the way you think from the foundation, where everything must be rechecked, remeasured, and re-understood, not based on what seems right, but on what is actually true. The question we started with, which sounded so simple that it almost required no thought, now returns with a completely different weight, almost a challenge to the way you understand the world. Do you really understand size? Do you really know what it means when we say a planet has a diameter of hundreds of thousands of kilometers? When we say a world like HIATP 67b can be larger than Jupiter but much lighter? And if you pause for a moment, if you are truly honest with yourself, instead of just repeating what you have heard, you will realize that the answer is not yes but no. And what is even more important is that you must accept that without turning it into a personal failure, because this is not your individual problem. It is a common human trait, a limit built deep into the way our brains work. You were not designed to understand these scales. You have no direct experience to attach those numbers to reality. You have never stood next to an object of that size. You have never moved through a space where those distances have physical meaning for you. And therefore, your inability to visualize them is not a sign of lack of understanding, but a sign that you are reaching the real limits of human perception. What is interesting, and also somewhat paradoxical, is that science does not try to erase that limit by making everything easier to understand in an intuitive sense. It does not try to turn a super puffed planet into an enlarged version of what you are already familiar with. Instead, it does almost the opposite. It keeps the full complexity of reality and gives you tools to describe it accurately without needing to turn it into something easy to imagine. This means that when you learn about the universe, you are not moving closer to a comfortable feeling, not the feeling of, I get it, the way you understand an object in a room. Instead, you are moving closer to accuracy. And those two things, comfort and accuracy, do not always go together. One of the hardest things to accept is that scientific understanding often does not bring an intuitive feeling. It does not give you a clear image in your head that you can grasp. Instead, it brings a different state where you know something is true, you can prove it, you can calculate it, but you cannot see it in a sensory sense. This can be uncomfortable and may even make you feel like you do not really understand. But it is precisely at that point that a deeper form of understanding begins to emerge, because you are separating yourself from the need for everything to fit intuition. And it is there that the real beauty of the universe begins to reveal itself. Not the simple, easy to understand beauty, but the beauty of consistency, of fundamental laws that can apply everywhere, even when their results look completely alien. When you look at planets like HATP 67b, you are not just seeing a strange object. You are seeing proof that the universe is capable of creating structures that go far beyond any template you once thought was normal. And that does not make the universe chaotic or meaningless. It makes it richer, more diverse, and far more interesting. There is a very natural human tendency to want everything to make sense in the way you feel it, to want numbers to turn into clear images, to want concepts to become familiar. But at some point, you must let go of that need, because that need itself becomes a barrier. It forces you to distort reality, to fit intuition, instead of adjusting intuition to fit reality. The truth in science is often simple at the deepest level. The relationships between mass, force, and energy do not change. They are consistent. They can be written as neat equations. But when those equations are applied under extreme conditions, to temperatures of thousands of Kelvin, to systems with weak gravity or strong radiation, the results can look completely non-intuitive, and that is not a contradiction. It is a sign that your intuition cannot keep up with the deeper simplicity of the laws. Science does not require you to feel comfortable. It does not exist to confirm your intuition. It exists to describe reality, and that requires you to be honest with the data, even when the data goes against your feelings. When you look back at the entire journey, from trying to visualize size, to realizing that density, gravity, temperature, and radiation all work in ways you could not predict, you begin to see a clear pattern. The problem is not that the universe is too complex, but that the way you initially tried to understand it was too simple and too dependent on limited experience. And when you adjust that approach, when you accept that intuition has limits, and science is the tool to overcome those limits, you not only understand more about distant planets, but you also understand something far more important, something almost fundamental. Understanding your own limits is the first step to truly understanding the universe, because only when you know you cannot rely on feeling are you ready to rely on evidence. Only when you accept that you cannot visualize everything do you open up the possibility of understanding things beyond imagination. And it is in that very moment, when you let go of the need to control reality with intuition, that you begin to see the world in a different way, not as you want it to be, but as it actually exists, a world that is not intuitive, not always easy to understand, but consistent, profound, and possessing a beauty that does not lie in familiarity, but in truth. If you want to continue exploring the paradoxes that make your intuition collapse, subscribe to the channel so you don't miss the next stories. See you in the next video, where we will continue looking at the universe in a way that is not intuitive at all, but more correct than ever.